Thank you. Good day, ladies and gentlemen. My cave mining experience began with Dennis Laubscher working in the asbestos mines of Rhodesia in the late 1970s, extracting asbestos from relatively small ore bodies by caving methods, block caving and sublevel caving. My next most significant body of experience in cave mining has been with Codelco, Chile, and mostly within the mining district of El Teniente, the El Teniente deposit. Today, I continue to learn from Codelco's cave mining experience, assisting the division Chuquicamata with the startup of the underground mining project. So, the principal objectives of the presentation today, the focus of my talk today, is the experience of Division El Teniente, which is actually a number of operations extracting copper and molybdenum from a vast deposit located in the Chilean Andes. Today, they are extracting at a rate of about 140,000 tons per day. And as you will learn during the presentation, that did not happen overnight. That did not happen over 5 or 10 years. It took decades to reach that target. To benefit from the lessons learned over the decades in the largely competent andesite rock mass, the Chileans call it CMET, it's best to comprehend the El Teniente mining environment in which their mining activities take place, the characteristics of the rock mass, and the geomechanics mechanisms at play in the response of the rock mass to the mining activities. And if we understand that, and others understand that, they can consider how relevant the El Teniente lessons are, and if so, how to utilize them. But if their rock mass is markedly different, El Teniente's experience may not be useful. But there are some general lessons in cave mining that I think are transferable from El Teniente's experience. There we go. The agenda today. The main areas of discussion, as you can see on the screen, encompass the mining environment, the history, geology, rock mass, and so on, the mining methods, and the associated problems of those mining methods, collapses, rock bursts, and ground control difficulties, and also the lessons that they have learned over the decades. And we'll conclude with how Teniente have found panel and block caving over the years, and the fact that they need to follow the caving rules. It's essential practice, not only for something, a creature like El Teniente, but also greenfield projects. Essential. Today, the difficulties that Codelco still suffer usually relate to the failure for their operational and technical staff to follow the caving rules. So caving rules are very, very important. Have to be well constructed, well understood, agreed by all, and implemented in a professional fashion. The illustration here is of the Seoul city. We call it the Christmas tree, Teniente Christmas tree. It's a World Heritage Site, and it indicates the distinct environment in which the El Teniente deposit is located. This Seoul city was constructed in 1905 by the American Braden Copper Company and housed the plant, the hospital, schools, and company workforce. Today, the Seoul processing plant remains, and it is in operation, and the buildings are used for offices, with a number of entrances to the underground mine nearby the Seoul city. When I first went to Teniente in 1990, they had plans to close the plant, the Sewell mineral processing plant. Today, nearly 30 years later, the plant is still going with the small ball mills that they have operational. They find it very difficult to shut the plant. I think they are emotionally attached to it somehow. As you can see from the top illustration, it's located in the Andes, and you can see the different rock mass lithologies that are there. In the central core, there's the breccia Braden. There's a dacite porphyry, which is a very hard and brittle rock mass, and various other porphyries and breccias that are in this very complex setting. They commenced mining in almost 200 years ago, more than 200 years ago, and they've taken out 1 billion tons of mineral, creating a volume of about 400 million cubic meters. And Teniente is currently working on 3 haulage levels. The uppermost level is providing a service for the open pit, which they started a decade or so ago, obviously on the upper levels. And they're producing about 50 million tons per year. And by now, the sheer scale of this operation, this deposit of Teniente, should be clear. It's about 2 kilometers by 2 kilometers by an unknown depth. And you can see in the slide there, on the lower illustration, the number of sectors that actually contribute to the production. This lower sector here is called Andes Sur, and that is from the new mine level. You can see the letters there, NNM, and above that is the Esmeralda sector, and above that Teniente Cuatro Sur, which has long since stopped producing. Other sectors, Diablo Regimiento and Dacita and the Reservas Norte, they have been and probably but so you can see there are a number of sectors, and they have different mining environments, and that is an advantage when you have problems in a particular environment. So the geological setting. Chile is a very long country. It's more than 4,000 kilometers from north to south, but it's very narrow. And the average width of the country is about 177 kilometers in this direction here. And Teniente is south of the main, the capital city, Santiago. And Chile is located in the South American subduction zone, where the Nazca plate is uplifting the South American plate. And this is forming the range of mountains known as the Andes. This activity, this tectonic plate activity, results in active volcanoes, as you can see here, the southern volcanic zone, active earthquakes, which funnily enough have very little impact upon the underground mine, very little impact at all. And this geological setting, of course, as you can see on the right-hand side here, results in a very young geological setting and comprising complex sedimentary, volcanic, of course, and metamorphic rock mass. Such activity gives rise to structures, very significant and continuous structures, as shown by the illustration on the left here. And you can see the extent of these structures, and also that the Teniente deposit is located within 2 very significant geological structures. and they give the environment for Teniente. This illustration here shows the Braden pipe, which has very little, if practically no mineralization whatsoever, and it's a breccia. And so within the Braden pipe here, there is very little structure, but in the ore body itself, in the andesite, you can see significant structures paralleling these major structures, and within the fault zone that the Teniente mine is located. This shows the Esmeralda undercut level. Okay, let's move on to the rock mass characteristics within the structural environment. So you can see the environment is very complex, and how to adequately characterize the Teniente complex rock mass has long been a subject of discussion for the Codelco geoscientific professionals and the many visiting consultants and people who undertake numerical modeling. Everybody has contributed to this development of the rock mass characterization, but none more so than the Chilean professionals themselves. From the early 1990s, rock mass rating systems, as you can see here, this is the Laubscher rock mass rating system, and you can see the classes extend from 2B down to 3B in rock mass strength. So they have used the rock mass rating systems in mining design, stability appraisals, and of course as input parameters to determine the key caving factors involved. And whilst utilizing these rock mass rating systems, the Teniente staff have always questioned their applicability to the distinct rock mass of Teniente. And so as a result of that, professional engineer Andres Bercevich focused on the fact that there are very weak veinlets within the andesite rock mass that surrounds this Braden pipe, and he characterized it by the frequency of those and related the frequency of weak veinlets and fault intensity as well to the actual behavior of the rock mass, and they find this is a better indication of how the rock mass behaves. So zone 6 is weak, and zone 1, which is the Braden pipe, in this sense, is a stronger and more competent rock mass. Now let's look at the magnitude of the field stresses. So the stress environment in which the mine is located, this is from information provided by Herman Flores and Antonio Kazulevich at the start of the century, and this hasn't changed that much. You can see that the principal stress here is 60 megapascals and the field stresses range from 45 the mine here to the intermediate 52, and indeed the new mine level is probably of the same kind of order. You may find that a bit strange, but you can see from the Andes here that the slope of the mountains are significant. So this side of the Teniente deposit, which is the east side, has what they call the mountain. You can see here the elevation is significantly greater than on this side. So that provides a range in operating conditions. And remember that the Teniente consists of a number of sectors on this side and a number of sectors on this side. And the sectors on the eastern side, they tend to have more problems because of the field stresses. And so another young Teniente engineer developed strength envelopes so that they could use in numerical modeling and mining design. And he developed from laboratory scale and over the years, looking at their observations and measurements, and they have developed this rock mass scale failure envelopes for the diorite, for the andesite hanging wall and the andesite footwall. The andesite footwall, you can see, is marginally weaker than the hanging wall. The footwall andesite is on the east, and the hanging wall lies here. So we are mining engineers. And mining is drilling and blasting in very simple terms. And so it's important to understand how the rock mass behaves in response to those mining activities. And of course, with the undercutting operation, we then rely on the mining environment to do the mining for us. But before that, we subject the rock mass to many blasting activities. So it's essential that we understand how the rock mass responds and degrades as a result of the mining activities. From construction, the development, to the cave initiation, and then subsequent mineral extraction, the mineral draw. So in order to minimize the adverse impacts of each mining activity, an understanding of the associated geomechanics mechanisms is vital, which can then guide mining design and subsequent implementation. As an example of understanding geomechanics mechanisms, even today, after nearly 20 years of using preconditioning, how to design it properly and in different rock masses is still a significant problem for the professionals to resolve in the Teniente and other mining environments of the Codelco mining divisions. So discussing this, we come to the godfather of modern geomechanics, Everett Hook. And I always like to think that if you follow what Dr. Hook says, you cannot go far wrong in mining in life. And so his views with respect to rock mass characterization and numerical modeling are very clear. There is always going to be considerable uncertainty in estimating in situ rock mass strength and behavior. And without experience of actual ground conditions, this is even obviously a very difficult task indeed. Consequently, this brings us on then to the modeling aspects. If we don't have experience of operations underground to observe and to measure the response of the rock mass, the assumptions that we have to make in numerical modeling, where there is no history of mining, his view is that it's unwise to put too much credence in modeling results. Nevertheless, provided there is a database of observations and measurements to support the calibration and verification of modeling assumptions, modeling can greatly assist mining design and its implementation. And it's an essential tool today. So let's have a quick look at the mining method. We look at these layouts and we think, they're relatively simple layout. But the problem with cave mining is the sequence of how we develop and how we actually initiate caving and how we follow that. You can see here on the left the Atlas Copco schematic, which shows an older layout, which is based on extracting the ore by train. Today, we tend to extract by conveyor haulage. And on this right-hand side is a very simple 3D schematic that I put together just to show you that whilst we are looking at these solid objects, drawing objects, they represent the blasts that are actually taken to develop. And this is the undercut blasting ring. And this is a very simple illustration of a draw point, and the important point in cave mining, the draw point brow. And it's important to realize that although these look solid, they are actually the empty spaces from which we draw the mineral. And it's the rock mass in between these objects that we have to learn how to look after and support, so that the mining environment is safe. And once it's safe, it can be very productive. So let's move on to the mining problem. Collapses have been a problem for Teniente and other mines for a number of decades, as you can see by this graph here. And these histograms represent the number of collapses that have taken place. And the frequency of these is illustrated here by the areas that have actually collapsed in the different sectors of El Teniente mine. Teniente Cuatro Sur, which lies above the Esmeralda sector, and also above the new mine level, which is underneath here. They suffered almost 120,000 square meters lost, but they still continued to produce because of the panel caving method that the Teniente has employed. It's very flexible. And you can see that the primary mining began in 1982, and nearly 40 years later, they are still mining primary ore, and they will continue to do so. But you can see that the production in primary ore increased throughout these years, over the decades. Meanwhile, Teniente was suffering all these collapses. They still managed to produce at an ever-increasing rate. And this graph shows 2011, they were producing about 125,000 tons per day consistently. Let me see if I've covered everything. So it took 3 decades to actually resolve the problem, and the control measures that Teniente developed over those decades was to manage the cave back of the cave as the cave was initiated and moved towards the overlying level. It's important to control how that cave back is shaped, because that develops the macro stress field in which the production complex, the undercut level, the production level are developed and have to operate. And the other lesson that was learned was to strictly follow the caving implementation rules, the shape of the front, the geometry, and always to keep moving. Once you stop mining activity in cave mining, significant problems can develop. So it's an incredible entity, El Teniente, and there exists in Division El Teniente a work ethic and a culture to deliver mineral to the processing plant, almost to the extent of it doesn't matter about the cost or practically anything else. You can see all these problems, all these collapses, and they still manage to produce and increase the rate of production. One thing to remember about El Teniente is that they've been mined for so long, and they've been going down in depth, and they always leave above them in the crater, above the sectors on the east and western side, the broken material of the production complex, and material that has come in from the side. And it's a significant resource, and it has a grade of 0.7% copper, which the mine can draw in times of production problems in 1 or 2 active sectors. Another key factor in favor of El Tenienente and Codelco is that as an organization, they have always been open to review by others, and they allow people to come up with ideas, criticize in a constructive way, and in that way they resolve problems. Wonderful organization in reality. So let's talk about the many factors, which is why it took so long for the engineers to come up with these solutions. You can see it's actually the geotechnical factors, the field stresses, the rock mass characteristics, the mining design, the layout of the draw point, the crown pillar geometry and design, the macro sequence, of course, a very significant factor to consider, and important that this is followed. Once you get the design and you are satisfied that it is a sound mining design, and you have identified all the caving rules, the shape, orientation of the front and so on, these must be they must be followed very strictly. And then the other factors can be broken down to ahead of the caving front and behind the caving front. Now, I've highlighted in this quite significant list really the most important, or the most significant in collapses: the mining design, how the macro sequence is designed and followed, and the abutment loading, of course, which loads the tunnels and the mining environment in the production complex, and how many open draw points ahead of the cave front in the panel caving method that the Teniente follow. And of course, behind the caving front, the only factors, the main factors that we have to control anything are the draw of ore, and that and the loading of the pillars that leads to. So the next problem that Teniente has suffered, also associated with primary ore. This graph shows the increase in primary ore over the years here. Illustrates the frequency of rock bursts that have occurred over time in the different sectors. And these here shows how Teniente have learned to manage the mining seismicity that takes place. It will never go away, but it's the management of it that allows them to continue to produce. Here we see the early part of this century and the rate of production, 125,000 tons per day, how they have resolved the problem of mining induced seismicity, very significant rock bursts. So they have managed this by preconditioning, by improvements in the mining method, and the realization that it's the geometry of the cave back that is really important in setting the stress environment in which the operations take place, and improvements in ground control, which we will look at just now. So they are able to operate with these control measures. Principle one being preconditioning and the control of the cave back, of course. But preconditioning actually conditions the rock mass to make it less brittle. And being less brittle, the magnitude of the events that take place is greatly reduced. So this illustrates here the use of hydraulic fracturing and how they actually position the hydraulic fracturing. Here it is positioned ahead of the caving front, and the preconditioning advances in this direction, protecting, weakening the rock mass ahead of the caving front. And they space the holes here 1.5 meters apart, roughly, and the radius of these is 20 to 30 meters of that kind of order. They then, having decided that this area was the important one, which is where most of the damaging events take place, they looked to protect the infrastructure which lies below the production level, and they began to introduce hydraulic fracturing with a greater spacing in this area. And of course, you look here and you say, oh, this area hasn't been preconditioned, and this is the big discussion. Is it necessary to precondition the crown pillars? One thing that I didn't mention here in this slide is that when in the Teniente Quattro Sur sector, which mined over a number of decades, when significant collapses occurred, they developed the technique to actually go beneath the production level, and they used the ventilation level to develop new draw points. And so when an area was collapsed, they went underneath and developed new draw points, and then they were able to produce and recover ore lying over a collapsed area. But it's not a significant rate of production, but it does enable some recovery to take place after collapsing. Let's go back. So the ground control improvements. Without improving their ground control, the success that they had in resolving collapses and rock bursts would have been less successful. The improvements in ground control over the years have been significant, and you can see the impact of that here. If we look at the capacity to absorb energy from rock bursts, we can see that over this time span here, again from 82 to 2015, Teniente have increased by 6 times the capacity of their support systems, and they did this by looking at the individual elements of a system. For example, the rock bolt consists of the bolt, the washer, the anchor, and the nut that actually holds the washer on. And once all these elements are designed to the system design and improve so that they can all provide the actual design strength, then the system is very effective and can actually absorb the energy dissipated when mining seismicity takes place. You can see in this slide here that they refer to shotcrete rain. Shotcrete rain occurred, and they observed this, and there was a fatality involved with it associated with shotcrete rain. In mining-induced seismicity, the shotcrete would fracture and lumps of shotcrete would fall, and this is called shotcrete rain. And the way that they got over this was to actually put an additional layer of mesh over the shotcrete, and then when mining seismicity occurs, the shotcrete fractures, but it is constrained and prevented from falling and injuring people and, of course, equipment. So, what are the key lessons learned over the years? Octavio Araneda and Andre Sugaret in 2007 highlighted these lessons. At that time, it was thought that wide caving fronts were the cause of the problems. They introduced advanced undercutting, which was a kind of fine-tuning of the mining design, and they figured that whatever they do, they will always face problems, so they always have to have a plan B and probably C and D as well. And follow the rules, quality and discipline, essential. And they considered at that time that mining control was not enough to manage the mining-induced seismicity. As a comment on these, today there is a sector in Teniente, Reno, Dacita, that is mining 1,000-meter caving front, more than 1 kilometer. So this was an erroneous conclusion. And advanced undercutting, they have moved back from that, and they like to follow a just-in-time development of the drawbells and the advance of the undercut, rather than follow the advanced undercutting variant, mining variant. Since that date, as you have seen from the presentation, they've introduced preconditioning to manage the seismicity. They've managed the cave back, and in that way, they have reduced the magnitude of abutment loading. They've learned caving rules, applied them, essential to follow them, and this improvement in ground support has led to much better conditions in the production level. And they are always questioning their assumptions about the rock mass behavior in the stress environment of the Teniente mine. And so, concluding remarks, it's a very complex mining method, although it appears to be very simple. And the design has to be closely linked to the implementation of cave mining. A very simple illustration of that is here. An objective-based mining design, you have to clearly state your objectives, follow this route path here, where you select a design and go through implementation. And during that implementation, essential that you monitor and observe, and with the observations and measurements, you can feed back into the actual implementation, but also with the lessons learned, go back into the engineering design, so that the design and the implementation in cave mining very closely linked. Very important to follow the caving rules that arise from the mining design, as we can see here. I highlighted brittle, competent rock masses. Preconditioning has a role to play there, but in other types of rock masses, it may not be relevant. If the rock mass is already fractured, why precondition it? Cave back management essential to protect the production complex. And so for greenfield, even brownfield projects, the advice will be to avoid aggressive extraction strategies, which usually arise from trying to achieve a good financial outcome. Never a good thing to follow, especially when you consider that all models are probably wrong. Some are useful. And if you imagine the assumptions that have to be made in financial engineering, they are maybe even wilder than some of the engineering assumptions about the rock mass. So accept that there will be a long-term learning curve. Remember, Teniente learned over 30 to 40 years how to characterize the rock mass behavior and invest accordingly. So why is Teniente successful? Well, they've got really well-educated professionals. As I've worked around the world, I've come to appreciate just how well-educated the Teniente workforce is. And they have a very good corporate culture, willing and open to adopt new techniques and to listen to other people. And of course, the people itself, the people who do the work, their work ethic and the generations of involvement of the families that live adjacent to and in the district of El Teniente. And finally, the number of sectors. They have a number of sectors that contribute to the production. A very important crater material, which is there as a contingency sector to cover the unexpected events. And finally, the recovery level that can be developed under a collapsed production level. Thank you very much for your time.
Thank you very much, Kevin. We have some time, so I actually have a question from you. I've been to El Teniente a couple of years ago, and I witnessed how enormous operation it is and how beautiful the environment it is there in those big mountains. And when I was part of meeting between Rio Tinto and Geotechnical staff, there was that kind of observation that in terms of development of block cave, seems like Rio Tinto has lots of experience in that area because they have developed many mines. However, there seems like Geotechnical has much more operational experience, especially in dealing with these high-capacity block caves. And there were lots of discussion about this hydraulic fracturing and preconditioning. And also this, as you also said about this aggressiveness of the production rate. So how you, what is your opinion, for example, on the production rate assumption on our Oyotl panel zero production rate? We are talking about somewhere 100,000 per day operation and reaching to this in significantly short time frame. Have you seen those plans, and do you have your own opinion on this? Because it is a greenfield mine in Mongolia, right?
Yes, yes. I briefly looked at the some presentations that were forwarded to me, and I would love to talk about one project that I'm working on at the moment, but I cannot. But as a general rule, if you have the opportunity to begin closer to surface and learn about the rock mass, for example, in the cross sections of OT, I see that there is an ore deposit closer to surface. I would. For me, my strategy would be, and I don't have all the information that you guys have, I would look to start there. I would look to produce at maybe 45,000 tons per day, get that operation going, 45,000 tons a day, learn about the rock mass, learn about how mining degrades that rock mass, and learn how to properly support it. And then with that production going, go underneath that and with all that knowledge that you have gained from the earlier time, begin mining in the harsher mining environment, supported by that knowledge, by the lessons that you have learned, how to approach mining in a new environment. It makes sense to do that. You know that you are going to be mining in OT for many decades. So that's why I say in the point here, invest accordingly. You have to accept. It's almost like an exploration, if you will, to accept that initially you are not going to be able to reach 100,000 tons in 6 or 7 years. So that would be the strategy that I would do. And I've recommended that, and in a number of places, and it's been ignored, and the results are evident. You pay the price if you try to go too aggressively. Look how long it took El Tenienente, and with that really wonderful workforce that they have there too.
Is this beeping sound from your end?
Yes, I don't know what it is. I don't think it's a bomb that's ticking. I hope it's not. We can ignore it, I think.
Okay, so let's continue after all these presentations. While that, maybe you check your battery of your laptop, if it is laptop.
Yeah. This is the first time in my life that this has ever happened, and of course it would happen, of course, during a very important presentation. Softball Murphy's law always applies. Always applies.
Okay, thank you, Kevin. Actually, before I leave you, I actually would like to mention that it is really impressive to hear that you have worked together with Labster and part of the development of this rock mass rating system.
Yes, it's in my mind now as we talk, as if it was yesterday. You know, it was a wonderful environment, and working with Dr. Laubscher. I actually did another degree there, and he was the supervisor, and Beniowski was the other supervisor. So I've been very lucky in my life to meet these giants, if you will, and to actually work with them. He was a lovely man. He's no doubt looking at us from above saying, "Shut up, Ferguson, let them get on with their presentation."
All right, thank you.
Thank you,
again. Yeah, meet again on the question and answer session.
In a couple of hours. Many thanks indeed. All the best.
Okay. Thank you.
Thank you.
Хэдүүлээ маш сонирхолтой хэлбэл сонслоо.
Very interesting presentation indeed.
The
Kodelko experience in block caving is very rich indeed. Many decades of experience and the various issues faced and resolved during all those years. And as the graph has shown us in El Tenienте, the production rate has been instead increasing. In the meantime, having faced this technical issues in the meantime, but resolved very effectively. So the timely resolvement of issues, very good practical, the resolvement of issues, you know, such experiences are very interesting, of course. RMR, the classification system as a student, and when we were studying the rock mass, the Russian system was taught to us. The Laubscher's classification, on the other hand, you know, the very practical, very pragmatic classification, good one. And our speaker had the honor of working with him. That very, very nice history indeed. And the Ferin Prince will present next. Again, panel first, panel one of North Hugo deposit, how design is done, in which issues are of utmost concern. You know, so that this will be some of his.
Good.